Good evening. There we go. Welcome. Welcome to the LaCasce Family Professorship of Natural Sciences inaugural lecture. This is once again one of the great moments in the life of our college where we get to celebrate great teaching and exemplary scholarship. Really remarkable time for us. This professorship was created by Professor Roy LaCasce in his will and is dedicated to the memory of his parents. Roy, as many of you know and some of you heard at dinner, was a Bowdoin institution. He was beloved by generations of students, many if not most of whom stayed in touch with him year after year. He came to Bowdoin as a student in 1940 and he essentially never left except for his time in graduate school and interestingly for a short stint in Beirut in the U.S. Foreign Service. He loved this place dearly, and we are deeply fortunate to have had him as a member of our community and deeply grateful for his enormous generosity. And this professorship is one example of that generosity. Our speaker tonight is Professor Stephen Naculich. He is Bowdoin's first LaCasce Professor of Natural Science, LaCasce Family Professor of Natural Sciences. Steve is an extraordinary scholar and teacher, and he is a magnificently deserving recipient of this high honor, and Roy would be so proud. Steve is a rarity in the world of physics, someone who conducts groundbreaking research and is internationally known for it in areas such as elementary particle theory and string theory. And at the same time, he devotes himself exclusively to the teaching of undergraduates. Last year, there were 14 physicists nationwide that were named Simon Foundation Fellows, and Steve was the only fellow who hails from a small liberal arts college. In fact, in all of the fellowships that have been given by the Simons Foundation over time, he is the only recipient from a small liberal arts college. He's been a visiting scholar at institutions like Harvard and Michigan. He is a speaker and a scholar who is in demand across the country, and his work has been supported by the National Science Foundation for over 15 years. He has remained a devoted and extraordinary teacher here and has been recognized for such in his time at the college. In 1995, he received Bowdoin's Karofsky Prize, which honors a young faculty member who, quote, best demonstrates the ability to impart knowledge, inspire enthusiasm, and stimulate intellectual curiosity. It is my great honor to welcome to the stage our LaCasce Family Professor of Natural Sciences, Stephen Naculich.
Thank you, Clayton, for those generous remarks. And thanks to all of you who are here tonight to help celebrate this occasion. I see lots of friends and colleagues on the faculty and students. This is great. You do know I'm going to talk about physics. Maybe you were fooled by the innocuous title. Well, I'm going to go on with introductory remarks for a few more minutes, so you can sneak out now if you need to. I'd like to acknowledge two special out-of-town guests tonight who came up from Worcester, Massachusetts for the celebration. My mother and father-in-law, Joanne and David O'Brien, who are sitting in the front row right here. Dave is an emeritus professor of history from Holy Cross College, and both he and Joanne have always been inspirations to me. I'd like to begin by expressing my gratitude to to President Rose and Dean Scanlon for naming me the LaCasce Family Professor, to my colleagues in the physics department who supported this, and of course to Roy LaCasce, whose bequest to the college funded this professorship in honor of his parents. I'll have more to say about him later. I'm honored and flattered to have been chosen the first LaCasce professor. But as grateful as I am for this honor, my real debt of gratitude to Bowdoin, and especially to the physics department, is for hiring me as an assistant professor 23 years ago. As many of those in this room know very well, the academic job market has never exactly been a cakewalk, but it seemed particularly challenging when I began to search for a job in the early 90s. In addition to the usual glut of qualified PhDs seeking faculty positions, The US was in the midst of a recession, and many top industrial labs like Bell Labs were shedding physicists who then decided they'd try their luck as teachers. Worse yet, the Soviet Union had broken up a year or two earlier, and many brilliant Russian and Eastern European physicists were seeking better job prospects in the West. In 1992, there was an article in the New York Times about the glut of physicists, and specifically about the record number of applicants for a single physics faculty position at Amherst College. Yes, I was one of those applicants. No, I didn't get the job. I had another strike against me. You see, I am a theoretical physicist. Most physicists can be classified as either experimentalists or theorists. Experimentalists are the ones who actually devise and carry out the experiments that probe the workings of nature. Theorists are the ones who take these experimental results, try to find patterns among them, interpret them in terms of mathematical frameworks, and ideally to make predictions that can be tested in new experiments. Both theory and experiment are an integral part of physics, and it used to be that physicists did both of these. But since about the middle of the 20th century, the skills required for both activities have become so specialized that a division of labor has emerged. Men and women are now trained to be either experimental or theoretical physicists, who then cooperate in a mostly amicable partnership to attempt to understand the physical world. Science departments at top liberal arts colleges, in addition to providing courses, place a lot of importance on providing opportunities for their majors to engage in research outside the classroom. For that reason, they understandably prefer to hire experimentalists who can set up labs in which undergraduates can participate. Often they have fun toys like high-powered lasers or dewars of liquid helium. Many of you were at Beth Stemler's talk last week, where she talked about the fancy mass spectrometers that she lets her students use. Some lucky students even get to accompany their professors to exotic locations like Greenland or Antarctica to study climate change. What can theoretical physicists offer students? Well, let me describe what the day-to-day research activity of a typical theoretical physicist looks like. Read a journal article. Stare at a blank piece of paper. Scribble something on it. Stare at the paper some more. Scribble something else. Frown at the paper. Tear it up and toss it into the recycling bin. Repeat. And drink coffee. Lots of coffee. Not so exciting. So you can see that it's more of a challenge for a theorist to engage students in their research. Not impossible, but definitely a challenge. I also think that experimentalists sometimes regard theorists as harbingers of bad luck. One of the most celebrated theoretical physicists of the 20th century was Wolfgang Pauli. Many of you may remember the Pauli exclusion principle from your chemistry courses. Less well known is the Pauli effect. When Pauli would go into the lab of one of his experimentalist colleagues, disaster would often occur. Experiments would malfunction or burn out. As a result, his friend Otto Stern banned Pauli from entering his laboratory at the University of Hamburg. Once, an expensive measuring device in a physics lab at the University of Göttingen suddenly stopped working for no apparent reason, even though Pauli was not present. Afterwards, the director of the institute wrote to Pauli at his Zurich address about this incident, mentioning that at least this time Pauli couldn't be blamed for the disaster. After a while, he received a reply in an envelope with a Danish stamp. Pauli wrote that he had gone to Copenhagen to visit Niels Bohr, and that at the time of the mishap, the train was stopped for a few minutes at the Göttingen rail station. The Pauli effect was at work. Now, there may have been a rational explanation for the Pauli effect. Pauli was a mischievous fellow, and it was observed that when he entered a lab, he would often head for the nearest set of switches on the wall and flick them up and down a few times. Some experimentalists combated this by installing Pauli switches near the door to their labs. These were basically a set of circuit breakers that weren't connected to anything. Anyway, I promised Madeleine Massol that I won't touch any of the switches in her lab, unless it's the switch of a coffee maker. So thanks again, especially to Dale Cyphers, Jim Turner, and Guy Emery for taking the risk of hiring a theoretical physicist. I have a real love and passion for both teaching and doing research, and Bowdoin, with its balanced emphasis on both, has provided the perfect environment for me. I have lots of wonderful colleagues in my department and out of it, and the excellent food here is an added bonus. I'm also grateful to Roy LaCasce for another reason, since the position into which I was hired was the one vacated by him upon his retirement at the age of 70. Okay. Yeah, it is. It was working earlier. Okay, sorry. Maybe I have to reboot this. I'm sorry, the computer is frozen up. This is really what I was talking about. I'm just rebooting. It was just frozen. I should have probably checked it. It worked at 3:30. Thank you. Proof. So, as I said, Roy LaCasce retired at the age of 70 and graciously made available the position into which I was hired. Roy continued, however, to teach after his official retirement, particularly a rather famous or infamous course called Methods of Theoretical Physics, or Physics 3000 as it is known to generations of physics majors. Now it's, sorry, Physics 300, now known as 3000, same course. At an event in 2008 celebrating Roy, Jim Turner gave a nice description of this course. He said, "The pace and level of difficulty of the course were almost perfectly right. The weekly homework assignments were very challenging, but not so challenging that with a considerable effort the challenge could not be met. Success in the course gave students a great sense of accomplishment, and because they had all faced the same challenge, a sense of commonality and bonding with their fellow physics majors. They had become part of the Bowdoin physics community, something that Roy always was actively promoting, both in and out of the classroom. After I had been at Bowdoin for about 5 years, Roy finally trusted me enough to let me teach Physics 300. And Thomas Baumgart and I, who now share the course, have tried to remain true to the spirit of the course. Roy always remained interested and would often sit in on the oral presentations at the end of the semester. Roy's association with the college goes way back. Both his father and uncle attended in the early 20th century. Roy arrived in Brunswick in 1940 at the age of 17. He graduated in 3 years because during World War II, Bowdoin had instituted summer sessions. Then at the ripe age of 20, he went off to the U.S. Naval Research Laboratory in Washington. He entered the U.S. Foreign Service and served briefly as vice consul in Beirut. He later obtained a master's in physics from Harvard and a PhD from Brown University, becoming an expert in underwater acoustics. He returned to Bowdoin in 1954 as an assistant professor and continued to teach until 1999. But Roy was always fond of recounting that his Bowdoin teaching career began much earlier. At the beginning of his senior year, the chair of the department, Noel Little, came to him and another senior and said, "We're a little shorthanded this term. Can you help out?" What that meant was that these students had the entire responsibility for the introductory physics lab course. So that's Roy in the middle. He's being rowed to classes, I guess, by his fraternity brothers. The drainage on the quad wasn't quite what it is today. I think that's called Lake Bobo. So here he is as an assistant professor. In addition to teaching physics, Roy was an avid figure skater. and was a test judge for the U.S. Figure Skating Association for 30 years. Here he is giving advice to some students on the ice. Roy had a tremendous influence on the college, and he fundamentally changed the fundamentally shaped the physics department and curriculum. But probably the most enduring legacy was his ability to connect with students. He took a strong interest in them, helping them not only to understand physics, but also giving them career advice. And he continued these relationships long after they graduated. When they came back for reunions, he would often entertain them with an hour of physics demonstrations, so-called fun with physics. In the late 70s, he instituted an annual department letter that was sent out to all physics alumni with news of what had happened in the department and the college over the previous year. He often added personal handwritten notes, and his former students often wrote back, keeping him apprised of their life beyond Bowdoin. As a result, there are very strong ties between the physics alumni and the college. I can only aspire to live up to his legacy. So first, a note about the title. When I was contacted in July for the title of my talk, I had no idea what I was going to talk about. So I had to come up with a title that was sufficiently general to cover pretty much anything I decided to say. So after a little thought, I came up with Simplicity and Complexity in Elementary Particle Physics. I discussed this with my colleague Thomas Baumgart, and he suggested that I drop the last part and just call it Simplicity and Complexity. That was even better because that covers just about anything that I would want to talk about, or anyone else for that matter. So who knows what you're going to get. But in fact, this talk will be about elementary particle physics because that's what I know about. I'm sorry if you were expecting something different. If you like subtitles, this is about the search for the fundamental laws of physics. The notions of simplicity and complexity can be understood in a number of different ways. For example, they could refer to the perceived difficulty of the subject. The simple is what is easy to understand. The complex is much harder. On these terms, most people regard physics as complex. When someone says of something, it's not rocket science, the implication is that what they're talking about is not that hard to understand, unlike rocket science, which is. On the other hand, physics students, after they've learned something in class, will often exclaim, "But it's so simple," or "It's so obvious." Sometimes this reaction only comes after they've been struggling unsuccessfully on a problem set for hours. Then suddenly they perceive a better way in which to think about the problem, and the answer becomes clear. It was much simpler than they had expected. One of the greatest pleasures of being a physics teacher, and my colleagues I'm sure would back this up, happens when we witness on the face of our students the sudden transformation from complete bafflement to enlightenment, usually accompanied by big smiles. Students aren't the only ones who have these sudden epiphanies. One of my favorite quotes is by Niels Bohr, one of the inventors of quantum mechanics, who said, "Tomorrow is going to be wonderful because tonight I do not understand anything." Well, I'm sure that many students can sympathize with the last part of that sentence. You just have to have the confidence that you will get there. That's what we try to do in Physics 3000. So I'd like to try to give all of you a taste of this experience. This is a demo that we sometimes do in our introductory physics course. Okay, so suppose I have two flasks. One contains a liter of water and the other a liter of red wine. Now I take 1 cup of the water and pour it into the wine. Then I take 1 cup of the wine-water mixture and pour it back into the water. Now I ask you, is there more wine in the water or more water in the wine? You might think that there is less wine in the water because the wine that I poured back into the water was slightly diluted. On the other hand, the wine-water mixture that I poured into the water represents a greater percentage of the total because there is less water in the flask. So it's a little complicated. In fact, you're probably starting to get a headache thinking about it, even if you haven't had any wine this evening. Let me show you the math. Okay. I realize if I start going through this, most of you are going to start heading for the door. Fortunately, there's a better way to think about this problem. I think you'll all agree with me that at the end of the process, there's an equal amount of liquid in both flasks. I took 1 cup of liquid from the water and put it into the wine, and I transferred 1 cup back. So they both have the same amount. So let's call x the amount of wine in the water, and 1 minus x the amount of water. In the right flask, let's call y the amount of water in the wine, and 1 minus y the amount of wine. Now, the other thing we know is that the total amount of wine is conserved. There was 1 liter to begin with. So if we add the two expressions for the amount of wine, 1 minus y plus x, that has to add up to 1. Now, even if you're a little rusty with your high school algebra, I think you can see that the only way to satisfy that equation is if x equals y. In other words, there's an equal amount of water in the wine as there is wine in the water. And now that you realize that it kind of had to be that way, because all I did was transferred a certain amount of wine to the water, or water to the wine, and an equal amount of wine back to the water. It has to be the same amount because I end up with the same amount of liquid in both flasks. So the problem that initially seems complex is actually quite simple if you think about it in the right way. Let's look at another take on the notions of simplicity and complexity. They could refer to the nature of the subject matter. On these terms, physics is definitely simple. It deals primarily with inanimate objects like planets, billiard balls, and atoms, which engage in simple, predictable behavior. Planets orbit, billiard balls move in straight lines, and atoms obey the Schrödinger equation, which is pretty simple. In my courses at Bowdoin, I mostly only have to deal with the very simplest atom, hydrogen, which contains 1 proton and 1 electron. I leave the harder ones like carbon, oxygen, and uranium to my colleagues and the chemists. So all I have to do is explain how 1 electron interacts with 1 proton. Simple. Well, maybe not so simple. It does take most of 1 semester of quantum mechanics to do that. Even the proton itself is not that simple. You see, it's not elementary. It's made out of 3 quarks interacting with each other and with the electron in a complicated way. Even quarks and electrons might not be that simple. If string theory is true, and I expect you've at least heard of string theory, particularly if you're a fan of the Big Bang Theory, if string theory is true, electrons and quarks might actually be extended objects, tiny filaments or loops. So all we have to do is understand string theory. Fields other than physics all deal with more complicated subject matter. Chemists not only try to understand all of the elements, but also how they form compounds, including giant polymers. Still, they only have to deal with inanimate objects. The subject matter of biology is living creatures, which are much more complicated to understand. And as if that isn't enough, psychologists have to study living organisms which have consciousness, and who know that you're studying them, which complicates things even more. Sociologists, anthropologists, and economists deal with whole packs of these self-aware living creatures, all interacting in complicated ways with each other. And political scientists, they have to figure out how and why those packs of self-aware living creatures will decide to vote in political elections. Compared with that, how hard can string theory be? But what I really want to talk about this evening is the simplicity and complexity of the laws of physics themselves. So here's a fair statement of what we try to do in physics, how we try to understand things. Complex behavior arises from the combined activity of many objects, each responding to simple forces. So for example, the pressure you feel when you squeeze a balloon is just the result of the collisions of the myriad gas atoms against the inner walls of the balloon. So the result can be complex even though the underlying causes are simple. Now, what are those simple forces that to which objects respond? In our introductory physics courses, we discuss many different types of force: gravity, friction, tension, pressure, buoyancy, etc. But it turns out that all of these forces are just manifestations of 4 fundamental forces, plus a little application of quantum mechanics. I have to put that in just for... So, isn't that great? 4 fundamental forces. Simple. I can count them on the fingers of one hand, and I don't even need to use my thumb. So if there's one thing I'd like you to take away from this talk tonight, it's the notion of 4 fundamental forces, which are all we need to explain all the phenomena in the physical world. So I need to tell you what these forces are and how that works. So first force I'm going to discuss is gravity. And now we begin a little historical tour of physics. But I must warn you, this is physicists' history, and therefore will be simple, maybe even oversimplified, not complex like historians' history. Isaac Newton first characterized the force of gravity mathematically. Many of you know the inverse square law. He also explained that gravity acts on both terrestrial objects, like apples, and celestial objects, like planets. Now, this was a novel idea at the time, since at first sight, terrestrial and celestial objects behave very differently. Apples fall toward the ground as a result of gravity, whereas objects in the sky mostly move in circles around the Earth, approximately once each day. Of course, we know that this motion around the Earth is only apparent, and it's actually due to the fact that the Earth is rotating on its axis once every 24 hours under approximately stationary objects. Still, it seems that celestial objects are immune to Earth's gravity, since they remain in the sky and do not fall to the Earth like apples. Now, an apple only falls straight to the ground if it's dropped. If it's thrown horizontally, it'll follow a parabolic arc. If it is thrown faster, the arc will be wider. This is an illustration from one of Newton's books. It shows that if you throw an apple fast enough, actually I think it's supposed to be a cannonball. You see the series of curves here, parabolic arcs, but then if you throw it fast enough, it actually will follow the curve of the Earth. And the apple would orbit the Earth once every 90 minutes, neglecting air resistance, of course. The moon moves around the Earth in a nearly circular orbit once every month, and Newton explained that this was basically a similar effect due to gravity. It takes a month because the gravitational force is so much weaker at its distance from the Earth. Remember the inverse square law. But it's not non-existent. Gravity also explains why planets orbit the sun and why the sun is in orbit around the center of our galaxy. This insight that both terrestrial and celestial objects respond to the same force and obey the same law was Newton's amazing feat. He also had amazing hands. Sorry about that. This was also one of the first examples of unification in physics. This brings up another facet of simplicity, which is economy of explanation. This principle is known as Occam's razor, after William of Ockham, who wrote, "Plurality should not be posited without necessity." Isaac Newton expressed the same idea by writing, "We are to admit no more causes of natural things than such as are both true and sufficient to explain their appearance." If you have to invoke a different explanation for every phenomenon you encounter, it's not clear whether you're actually explaining something or just describing it. It's far more compelling if a single principle can explain a diverse range of phenomena. In other words, less is simpler. Einstein expressed a similar sentiment: make things as simple as possible. Now, in the public mind, Einstein is almost synonymous with complexity, but physicists know that his insights were almost always marvelously penetrating and simple. Einstein added a cautionary note, but no simpler. You cannot ignore the irreducible complexity of what you were dealing with. So this is what I'm going to try to do in my talk. I'm going to try to make things as simple as possible, but hopefully no simpler. Einstein, like Newton, was a unifier. In 1905, in his theory of special relativity, Einstein described how space and time are unified into the single concept of space-time, and he showed how Newtonian laws of motion must be modified when objects are moving at speeds close to the speed of light. Einstein also improved on Newton's theory of gravity. Exactly 100 years ago, he explained that space-time is actually curved, and that this curvature is responsible for the force of gravity. This gave a deeper and also more accurate understanding of gravity. For example, the bending of light near a massive object. Now, the mathematical description of curved space-time is somewhat involved, and the equations that Einstein came up with to describe gravity are a little bit more complex than Newton's. Don't worry, I'm not going to make you solve these ones. In fact, perhaps Thomas Baumgart will explain these in more detail in his public lecture next February, so I'm not going to say any more about them. But let me just add that while general relativity is wonderfully complex in its mathematical formulation, the central idea behind these equations is beautifully simple. They were well expressed by John Wheeler, who said, Space-time tells matter how to move. Matter tells space-time how to curve. That's what those equations say. So that's gravity. Another famous example of unification in physics took place in the 19th century. The electrical force acts between objects possessing something called electrical charge, which comes in negative and positive varieties. The electrical force causes charges with the same sign to repel, but with opposite signs to attract. The force between them obeys an inverse square law called Coulomb's law, which is reminiscent of the inverse square law of gravity. Now, a completely different type of force, the magnetic force, causes magnets to attract iron filings and compasses to point to the north. It also causes two current-carrying wires to attract or repel one another with a force that looks like this. Like celestial and terrestrial gravity, these magnetic and electric forces were understood to be completely independent until the 19th century, when connections began to be noticed between them. We've already seen that a magnetic field can be produced by a current that is moving electrical charges. Michael Faraday discovered that conversely, a changing magnetic field could produce an electrical current, the principle that underlies most electrical power generation. But it was James Clerk Maxwell who went a step further and completely unified these two forces in a single framework called electromagnetism, and discovered the equations that bear his name, Maxwell's equations. These equations may look somewhat complicated, but the beauty of them is that they subsume such a large range of phenomena that had been previously understood as separate. What's even more amazing is that we now understand electricity and magnetism to be tied together in the same way that space and time are unified into space-time in special relativity. In fact, Einstein came up with special relativity by pondering the consequences of Maxwell's equations. His 1905 paper was entitled On the Electrodynamics of Moving Bodies. So we've tied these two things together, electricity and magnetism. But there was an unexpected bonus. You may know that when you have several equations in several variables, you can often combine the equations to eliminate some of the unknowns. You can do the same with Maxwell's equations. So Maxwell's equations involve the electric field E and the magnetic field B, but we can combine these equations to get an equation just for E and an equation just for B, the electric and magnetic fields, and they look like this. Students of physics will recognize these as wave equations. So what Maxwell discovered was that his equations predicted the existence of traveling waves. And furthermore, the speed of these waves is given by, well, this expression here, 1 over the square root of epsilon naught mu naught. Now let me just go back a bit to see what those are. So when we looked at the force between two charges, the electrical force, there was a constant epsilon naught here, and that sort of characterizes the strength of that force. The constant characterizing the force of the magnetic forces is mu naught. See, it's easy to remember because epsilon and mu are Greek letters for E and M, so easy to remember. Since these two forces are unified in electromagnetism, it makes sense that the waves would travel at a speed that depends on both of them. Epsilon naught here, this is called the vacuum permittivity, doesn't matter. That's its value, you get that from experiment. Similarly, measuring the force between wires, you get mu naught. And since I suspect that most of you probably left your calculators at home tonight, I'll do the math for you, multiply those together, and take the square root, and we get 2.998 times 10 to the 8th meters per second, about 186,000 miles per second. That is fast. But I hope you recognize that number. I hope that rings a bell. That is the speed of light. All right? So Maxwell wasn't trying to describe light, but unless there's a crazy coincidence going on here, Maxwell discovered that light is actually an electromagnetic wave. And not just light. Light is only one electromagnetic wave of a particular wavelength. There are also radio waves, microwaves, and X-rays. Shortly after Maxwell's discovery, Heinrich Hertz demonstrated the existence of radio waves with wavelengths from 1 meter to hundreds of meters, which soon began to be used for communications. Also used for communications and for cooking food as well are microwaves with wavelengths of a couple centimeters. A few decades later, X-rays were discovered, and of course these are now used for medical diagnostic purposes. These are all, X-rays are electromagnetic waves at the other end of the spectrum with wavelengths the size of an atom. So all of these tremendously useful phenomena and more are described by Maxwell's equations. Now, when we want to describe objects that are very small, like atoms and X-rays, we do need to use quantum mechanics rather than classical mechanics, but it's still the same forces at work. So I hope that the mantra of this talk is clear. By simplicity of the laws of physics, I mean unification, reducing the number of fundamental concepts and forces required to explain a wide range of phenomena. So far, we've reduced, so simplicity is unity. So far, we've reduced everything in our experience to two fundamental forces: gravity, described by Einstein's theory of general relativity, and electromagnetism, described by Maxwell's equation, which also we get light into the bargain. Now, the equations that describe these forces may not look all that simple to you, although I would argue they're about as simple as you could expect given what they're trying to do. But it's hard to argue with the economy that we've achieved. Two forces. Well, can we go further? Can we unify these two forces? Well, Einstein thought so. He said, the intellect seeking after an integrated theory cannot rest content with the assumption that there exist two distinct fields, totally independent of each other by their nature. He was talking about the gravitational field and the electromagnetic field. And there are some similarities between them. We already saw that Newton's law of gravity and Coulomb's law are both inverse square laws. In the 20s, Theodore Kaluza and Oscar Klein attempted to unify these two forces by looking at curved space-time in 5 dimensions. An interesting idea, right? It's the 5th dimension that gives you the electromagnetic field. And Albert Einstein himself tried for years, I mean, for almost 30 or over 30 years, to develop a unified field theory combining general relativity and electromagnetism, the two forces that we've met so far. Now, these attempts were all very tantalizing, but they ultimately failed for the simple reason that they didn't take account of all of the fundamental forces. They just had 2 of them. I told you at the beginning there are 4, right? Okay. There are 2 more forces to contend with, both associated with the nucleus of the atom. So basically the problem was Einstein was trying to make things simpler than possible. Okay. So early in the 20th century, it was established that atoms consist of electrons orbiting nuclei. Here's a nucleus. By the 1930s, it was understood that the nucleus consists of protons and neutrons. So here's lithium-7, 3 protons, 4 neutrons. Notice that whenever a physicist draws a picture, it's always a circle. That's because we're really lousy at drawing, so. The protons are positively charged and the neutrons are neutral. So the electrical force causes the protons to repel each other. The attractive gravitational force between them is so tiny as to be negligible. So you see we have a problem here. This whole nucleus should blast apart due to the electrostatic repulsion between the parts. It's actually even worse if you look inside the proton and neutron, which, as I mentioned before, consist of quarks. We call them up quarks and down quarks. So the quarks themselves are electrically charged, and so there's a repulsion going on there. So even the proton is not stable. What holds this whole mess together? It can't be the forces that we know. It must be some new force. Well, it turns out that besides electrical charge, quarks possess another type of charge. In fact, 3 different types of charge, which, just for the sake of convenience, we'll call red, green, and blue. These have nothing to do with the actual colors. They're just whimsical names that physicists give to these charges. So we've got 3 new types of charge. And like electrical charges, oh, there we go. Color charges attract their opposites. So red attracts anti-red, green attracts anti-green, and so forth. But there's a new feature. It turns out that the different colors also attract one another, so that a red, green, and blue quark together form a bound unit. This is a very strong force, and it's what holds the quarks together inside the proton and neutron, much stronger than the electrostatic force. The color force also leaks out from the proton and neutron slightly and causes the protons and neutrons to attract one another inside the nucleus. So this is called, this is the strong nuclear force, which is just, chromodynamic force is just Greek words for color and force. But the thing is, the strong nuclear force is a short-range force. It doesn't extend very far past the edge of the proton. So as a result, very large nuclei are unstable. Okay? When the nucleus gets big enough, the electrical repulsion between the protons outweighs the strong nuclear force. That's because the short-range strong force only acts between relatively neighboring protons and neutrons, whereas the electrical repulsion acts between all the protons. So as a result, in the end, the electrical force wins out. So as a result, a large nucleus can lose little pieces. This is known, this is the phenomenon of radioactivity, the instability of the nucleus, which was discovered in the late 19th century by Henri Becquerel, Marion Pierre Curie, Ernest Rutherford, and others. Later, in 1939, Lisa Meitner and others realized that as a result of this instability, large nuclei can sometimes even split into two approximately equal-sized smaller nuclei, a process known as nuclear fission. This knowledge was soon to change our world as it made possible the construction of both nuclear power plants as well as nuclear weapons. The instability of large nuclei also explains why there are only about 100 elements in the periodic table. Uranium is the heaviest naturally occurring element, and it is itself unstable. So chemistry students have that to thank for the fact that they don't have to memorize even more elements, right? Now, it's not just large nuclei that are unstable. It turns out that even smaller nuclei are sometimes unstable. For example, carbon-14, which is used in archaeological dating. In fact, it turns out that even a neutron, if it's outside the nucleus, is unstable and decays in about 15 minutes. So a neutron will decay into a proton, an electron, and an antineutrino. 15 minutes is only an average. Some neutrons last longer, some last shorter, but they don't last for very long. Now, this instability requires yet another force, and that is the weak nuclear force. Now, I call it a force, but it's more probably accurate to think of it as an interaction because instead of acting to repel or attract, it allows particles to change their identity. So it allows the neutron to turn into a proton and therefore decay. So we finally met the full cast of characters, 4 fundamental forces. So here we are. We've got to that point. We have gravity, which is weak and long range. Now, let me just say a word for why I say gravity is weak. You probably think gravity is pretty strong, particularly if you're near a black hole. But in fact, the gravitational force between 2 protons is minuscule. It's hardly, it's just tiny. The only reason that we notice gravity is because it's cumulative. And so it's only when you get together enough protons, like, for example, all the protons in the Earth, that there's an appreciable gravitational force being exerted on me, for example. Electromagnetism, I mean, if you think about it, even that force is easily defeated by a puny little refrigerator magnet, right? The magnetic force from a magnet has no problem holding up against gravity. So gravity is very weak, and it's a long-range force. Electromagnetism is much stronger, and it's also a long-range force. The strong nuclear force is, as you'd expect, strong, but it's short range. It only acts between sort of neighboring protons and neutrons. And the weak force is weak and also short range. To date, these are the only known fundamental forces in nature and are in principle responsible for all phenomena. There may be other forces, there probably are, but we have no evidence for them yet. So pretty much that's the whole game, just a question of putting them together. I could say a lot more about each of these forces, but the focus of this talk is on simplicity. So you might be asking yourselves, can we unify these forces even further? I mean, 4 forces is pretty good, but we're greedy. 3 would be even better. There's no guarantee this is possible, but we got to at least try. So let's play a little game and try to guess which of these forces we might try to unify. Well, you might try to unify the 2 long-range forces, gravity and electromagnetism, but Einstein worked on that for 30 years without much luck, so I think we better give that one up. Well, how about the 2 short-range forces, the nuclear forces? Can we unify those? Well, they're pretty different. How about the 2 weak forces, gravity and the weak force? No, it doesn't do any good. Well, electromagnetism and the strong nuclear force are due to attractive and repulsive charges between charges, so maybe we can unify those. Now, this is the most unlikely pair, right? Electromagnetism and the weak nuclear force are very different. One is medium strength and long range. The other is weak and short range. But there is a little clue here. The weak nuclear force doesn't just act on particles in the nucleus. The neutron decayed to a proton, electron, and a neutrino. So the electron is actually involved in both the electromagnetic and the weak force. And as you're probably guessing by now, this is where we finally succeed. In 1967, Stephen Weinberg and Abdus Salam independently succeeded in unifying electromagnetism and the weak nuclear force into what we now call the electroweak force. So now we're down to 3. Gravity, strong, electroweak. But you may be thinking, wait a minute. I just spent a while telling you how different these two forces are. How is it that they're actually the same force? Another way to put it is, if they originate from the same force, what accounts for the huge differences between them? What breaks the symmetry between the electromagnetic force and the weak force? And the answer is the Higgs field. So what's the Higgs field? The Higgs field is not a new force, but it's an entity that pervades all of space-time. Now, if that seems strange to you, I'll just remind you, we've already talked about fields, the electromagnetic field, when we talked about Maxwell's equations. So a field is something that exists in space-time, filling space-time. Electromagnetic waves correspond to vibrations of the electromagnetic fields. When there are no waves, the electromagnetic field is quiescent. Okay? There are no waves. The field is quiescent. It's a state of no energy. We call that the vacuum state. Nothing, right? What could be simpler than nothing? Well, it's the same way with the Higgs field. When it's quiescent, we're in a state of lowest energy. But now I have to tell you a little bit about what the energy of the Higgs field looks like. We can describe its potential energy with a shape that looks something like this. Kind of looks like a hat. This is the potential energy of the Higgs field. Now, let me talk about the symmetry of this hat. So this has a nice symmetry. If I rotate it around the vertical axis, it doesn't change the shape of it. It looks the same. If I were to attach a pom-pom right at the top and rotate it, it would still be symmetric, nicely symmetric. If I put a pom-pom down here in the valley of the hat, though, and then rotate the figure, the pom-pom would move to a different position. So putting a pom-pom in the valley breaks the symmetry. It would also look pretty stupid. Now, instead of a pom-pom, think of a marble. If I put a marble at the top, I might be able to balance it there, but more likely it's going to roll down into the valley because points in the valley have lower potential energy than at the top of the hat. So what does all this have to do with the Higgs field? Well, the quiescent state of the Higgs field, right, the state of the vacuum, is the state of minimum energy. But the state of minimum energy is in the valley of the hat, down here. And that state breaks the symmetry. So that's just a way of saying that the Higgs vacuum breaks the electroweak symmetry, right? The vacuum is a state of lowest energy, but the state of lowest energy is down here in the valley, and any point in there, you have to pick one point. It can be there or there or there, but you break the symmetry. It's no longer rotationally symmetric. And it turns out that symmetry breaking is what causes the weak force and the electromagnetic force to differ. Without the Higgs field, the weak force would be medium strength, just like the electromagnetic force. With the Higgs field, the weak field becomes short range and weak, whereas the electromagnetic force remains long range. So this is known by we call it spontaneous symmetry breaking. I'm leaving out a few details here, but the idea is it's about symmetry and the breaking of symmetry, and that's actually kind of remarkable. So it's the Higgs that's the problem, or the opportunity. So remember, when we unified the electric and magnetic forces, we got a bonus, right? We found that we got electromagnetic waves. Now, here too we get a bonus. The Higgs boson. Who's heard of the big Higgs boson? Okay, that's good. I was going to say, if you hadn't, I would ask you if you'd heard of the God particle. It's the Higgs boson. So you may remember that when Maxwell unified the electric and magnetic forces, he got this bonus of the electromagnetic waves. Electromagnetic waves are what happens when the electromagnetic field vibrates. Now, at the quantum level, electromagnetic waves correspond to particles. So there's this thing called wave-particle duality. So you have a wave, and then you get a particle. I'm not going to try to go into that, but these particles are called photons. And we can observe photons. We can measure them. What happens when the Higgs field vibrates? Okay, let's go back. So what do I mean by that? So you've got this marble sitting in the bottom. If it's just sitting there, it's the vacuum state. But you could imagine it rolling up and down the sides of this valley, back and forth like that. That would be a vibration of the Higgs field. And that vibration would correspond to something we could call a Higgs wave, although no one calls it that, because these waves are also particles, and these particles are the Higgs boson. So it's the vibration of the Higgs field up and down the sides of this valley that leads to the existence of a new particle called the Higgs boson. And because it costs energy to go up and down the valley, the Higgs boson has a considerable mass. It's a very heavy boson. So the electroweak force predicts the existence of these waves, these particles called Higgs bosons. Where are they? Well, because they're so heavy, they're very unstable. In fact, they only last about 10 to the minus 22 seconds. So it's not like these Higgs bosons are just lying around waiting to be observed. To observe a Higgs boson, you first have to create it. That sounds like a job for a particle accelerator. This is the site of the Large Hadron Collider, or LHC. You can guess that it's in Switzerland because those are the Alps in the back. The red circle here, about 17 miles in circumference, indicates the location of the tunnel, which is a couple hundred feet underground. Here's the tunnel. Someone walking down the tunnel. It takes a long time to walk around that tunnel. In the tunnel, they put a beam pipe, which is basically everything's evacuated out of it, and then they basically they accelerate protons down the beam pipe to very close to the speed of light. Now, other protons are accelerated down the beam pipe, but in the opposite direction, and then they smash together in a head-on collision. It's not like a demolition derby. And this is sort of what happens when you smash them together. The energy of the collision is converted into the rest energy of new particles. So particle accelerators are essentially particle creators. You're converting kinetic energy into rest energy. And the more massive the particles that you want to create are, the more energy you need. That's why you need such a mammoth machine to create Higgs bosons. The LHC, oh, I didn't show you this. Oh, after you create them, you have to look for them. And so you have to create very sophisticated detectors. And here are some pictures of the detectors. You see the person down here. That gives you an idea of the size of this detector. Here's another one. Very beautiful, beautiful detectors. Okay, so after 10 years of construction, the LHC finally went into operation in 2010 and began collecting data. And in the summer of 2012, from about 1,000 trillion collisions, a tiny fraction of the events had created Higgs bosons, and an even tinier fraction were subsequently observed, and they were found to have a mass about 133 times the mass of the proton. So this is fantastic, right? We've actually, the electroweak theory predicts these new particles, and they were discovered. This served as a final confirmation that the electroweak unification was the correct way of going. So finally, we've reached our present understanding of elementary particle physics. The strong and electroweak forces basically act among about 17 fundamental particles. I've put a dashed line around it because I haven't actually unified these forces, but they do live together in harmony. I haven't included the force of gravity because, for two reasons. First of all, we don't really understand it sufficiently at the quantum level. And secondly, it's not a truly quantum theory. And secondly, it's so weak compared to the other forces that it has absolutely no effect on accelerator experiments. Now, the standard model was essentially in place by 1973. And since then, it has been stringently tested, culminating in the discovery of the Higgs boson in 2012. Now, here's the good news. Every experiment done since 1973 has confirmed in detail the validity of the standard model. Well, okay, except that neutrinos, there are neutrinos, it turns out they have a small but non-zero mass, but it's not too hard to tweak the standard model to include massive neutrons. So this is an amazing success. Now, don't get me wrong. There are lots of things we don't understand. There are lots of results of experiments that we theorists don't know how to calculate. So just as one example, I told you the proton is made out of 3 quarks. So in principle, we should be able to calculate its mass since we know the force between the quarks, but we don't have any idea how to do that. Well, we don't know how to do it accurately. But anything that we can calculate agrees spectacularly well with the data. On the other hand, there are a lot of questions which the standard model doesn't even provide an answer. For example, I told you there were 17 fundamental particles. We have no idea why there are so many different types. We don't know why some of them are so much more massive than others. For example, the Higgs boson. We don't understand why the neutrino has any mass at all. And then there's gravity. To get answers to these questions, we need to go beyond the standard model to get to a more complete theory. So the standard model is excellent. It agrees with all the experimental data, but it's not the final answer. But the problem is this. Here's the bad news. Every experiment done since 1973 has confirmed in detail the validity of the standard model. So nature is not providing us many clues with how to go beyond it, right? Theory desperately needs experiment to guide it. So we're all really hoping that in the next few years, new phenomena will be discovered at the LHC or in other types of experiments that will provide some hints to help us formulate a theory beyond the standard model. Since we don't have any data to do that with, let's at least continue with this notion of unification. Can we unify these forces any further? Okay. Well, the ink had hardly dried on the standard model when Sheldon Glashow and Howard Georgi came up with what was called the grand unified theory. They want to unify the strong force and the electroweak force. And of course, the same question comes up. If we've unified these, what breaks the symmetry between them? Well, we need new Higgs fields. And with new Higgs fields, you get new particles, new Higgs-like bosons. The problem is, unlike the Higgs boson that we just discovered a couple years ago, these new particles lie far beyond the range of direct detectability, about 10 to the 15 GeV. So a GeV is about the mass of a proton. So this is 10 to the 15 is 1 with 15 zeros. Okay, so that's way more massive. Just to give you an idea of the LHC, it gets up to about 1,000 or 10,000 GeV. So we're talking about 11 orders of magnitude. So it might seem that it would be completely impossible to ever test the grand unified theory. But fortunately, it's not so, because grand unified theories also predict a new superweak force. Aha, we got a new force. Where did this new force come from? We start with this grand unified theory. You break the symmetry with the Higgs field, and you get the strong force, the electroweak force, and this new superweak force. And just as the weak force causes neutrons to decay, okay, remember when I introduced the weak force, it was really a transformative force that caused particles to change identities. Neutrons can decay to protons in about 15 seconds. The superweak force would cause protons to decay. The proton could decay into a positron and a pion. Okay? So according to the standard model, the proton is, in standard model, the proton is absolutely stable and will never decay, which is why they say diamonds are forever. But according to the grand unified theory, all protons will eventually decay. The difference is that while neutrons have a lifetime of only 15 minutes, the protons would have a lifetime of about 10 to the 29 years. Now, the age of the universe is only about 15 billion years. That is 10 to the 10. So you might think that this would be too long for experimentalists to observe. I mean, who has that kind of time these days? But as I mentioned earlier, with the neutron, lifetime is only an average. Some protons would take much longer to decay, but others could decay in a much shorter time, and a very small number would decay in the next hour or the next year. You just need to watch a lot of them. Well, to cut to the chase, experiments were mounted to try to detect proton decay, and they were not found to decay. It turns out that the lifetime for this decay is actually at least 10 to the, well, it's about 10 to the 34 years. So you don't have to worry about your diamonds, at least for now. So what we've just discovered is this theory doesn't work, right? It's ruled out by experiment. Experiment has shown that this prediction is not verified. Theory should be no simpler than possible. It's too bad. It's a beautiful theory. So anyway, that's an attempt at unification that didn't work. Now, I've been ignoring gravity for a while because we don't have a good quantum theory for it. But if we want to have a true picture, a full picture of all the forces, we need to include it as well. And to do that, we need to do two things. Well, we need to quantize it, first of all. This is sort of a to-do list here. In the morning, I'll quantize gravity, and then and in the afternoon, I'm going to unify gravity with the other forces. Okay? Well, it turns out there is actually a possible candidate for this, and it's called superstring theory. Let me tell you a little bit about it. Let me check the time. Oh, good, I still have 2 more hours. So superstring theory is, well, there are a lot of people involved in its creation, but John Schwartz, Michael Green, and Edward Witten are 3 of them. And what's the idea behind string theory? I'll be very brief here. String theory says that elementary particles like quarks, electrons, and photons are different modes of tiny strings or loops. They're not point-like particles, they're little loops. Now, what difference they're very small, so you generally don't notice any difference between them. They basically, to all intents and purposes, when I say really small, let's see, what is the figure here? 10 to the 19 times smaller than the smallest thing we can observe, okay? So, really small. So you might think, what difference does this make? How could that change anything? Well, it does change things. In field theory, which is what the Standard Model is based on, forces are mediated, these forces we're talking about, by the exchange of particles. So for example, we've got these 2 particles here. This is time flowing upward. And then there's an exchange of a particle between them, and that results in a force between these 2 particles. That's really what forces are at the quantum level. Now, if we're talking about electromagnetism, this particle is a photon. If we're talking about the strong nuclear force, this particle is a gluon, okay? If it's the weak force, these particles are called W and Z bosons. If this force were gravity, this should be a particle which we would call the graviton, but the problem is the field theory of gravitons isn't quite self-consistent. When you try to calculate things with it, you get nonsensical results. So that's what when I say that gravity, there's not a good quantum theory of gravity, that's really what I'm talking about. But in string theory, you have strings moving up through time, and they exchange a string between them. See, it's a very elegant idea, right? Strings exchange strings. And it turns out that I told you these different particles are modes of this string. So this string going across could represent all different types of particles. It could represent photons, it could represent gluons, and it could represent gravitons. In fact, it has to represent gravitons. When you work out the mathematics, one of the modes that's exchanged between these 2 strings necessarily has to be a graviton. So not only does string theory provide a possible quantum theory of gravity, it requires it. And it also requires other forces as well. So I hope you realize what this means. What I'm saying is the exchange of strings could account for all of the forces, right? String theory could be the theory of everything. See, all 3 forces we have, and they're all unified because it's all string theory. This is a wonderful idea, but is it true? We don't know yet. We really don't know, because to test it, you have to come up with some predictions. Now, string theory predicts new phenomena at an energy scale far beyond the range of direct experiment, 10 to the 19 GeV. So that's, that's a very large. You're never going to build an accelerator to test that. And in fact, some people have criticized string theory as being untestable because you could never mount experiments to test this. But the same thing was true for grand unified theories. They said that there would be new particles at 10 to the 15 GeV. Those were equally untestable. So that is, it's the same idea, except that in the case of grand unified theories, it predicted something else, namely proton decay. And you could test proton decay. So what you probably want to know is, does string theory predict anything testable like proton decay? And I wish I could say yes, but we don't understand it well enough to tell. String theory is tremendously complicated, I'm sorry to say, more so than grand unified theories. And so we are still trying to understand its ramifications. In fact, we're probably still missing a few key ingredients to this theory. It's not just that it's technically, it's just not that it takes a long time to calculate it. We don't even know how to begin to calculate these things. So it's a great idea, and we're hoping that this may be the theory of everything, but it's really too early to tell. So that's where we are. I'm going to just finish with one interesting feature of string theory, and that is that it predicts higher dimensions. Now, we met higher dimensions earlier when we were talking about Kaluza-Klein theory, when we were trying to go to 5-dimensional spacetime. It turns out that superstring theory predicts 10 dimensions for spacetime. Now, what on earth does that mean? So this line here is one-dimensional. It goes on forever in one dimension. This plane is two-dimensional. The world around us has 3 spatial dimensions and a time dimension, so 4 dimensions altogether. So it would seem like a prediction of 10 dimensions flies flatly in the face of that observation. But the thing is, string theory doesn't say that the dimensions have to be infinite. Some of them can be small. What do I mean by a small dimension? Well, here is a circle, which is one-dimensional, but it's finite, right? I mean, you can go around and come back to where you started from. And a cylinder is really a two-dimensional object. It's just a plane that's rolled up with one big dimension, one large dimension, and one small dimension. Now, in a quantum mechanical theory, the small dimension would be invisible at small energies. So this would look like it was just one-dimensional, like a line. So superstring theory prediction of 10 dimension could work, provided that we could explain why 4 of them are big, the ones we observe, and 6 of them are small. We have to come up with a way of compactifying 6 of the dimensions. We have to break the symmetry between them. There's 10 dimensions, but there's a symmetry that is broken so that 6 of them are different from 4 of them. Now, much research has been done on this problem, and we've learned a lot about compactified spaces. But I'm afraid that we're not actually all that much closer to answering this question than we were 20 years ago. So the verdict is still out on whether string theory does describe the real world. So I can't tell you whether it's correct, but it's certainly an intriguing idea, and it certainly unifies everything. So I think it's time to bring this talk to a very quick end. You'll all be happy. So let me see if I can summarize this. Elementary particles has become much simpler, that is to say, much more unified. It's also become more complex in its mathematical formulation. And I'd like to finish with a nice quote that Mary Lou Zaman sent me a few days ago. It's by her father, the mathematician Christopher Zaman, who said, "Technical skill is mastery of complexity. Creativity is master of simplicity." Thank you very much. I'd be happy to take any questions. Maybe we'll just have a few since we're running over a little bit. Oh, it's completely. Oh, Bruce? Is there only one type of string? No. There are open strings. There are closed strings. There are 5 different types of string theory, but they are all unified into a single framework called M theory. I could go on for about 2 more hours. But since we don't know, well. Michael? Oh, that's much more serendipitous. Because string theory was originally developed to not understand gravity, but to describe the strong force. Okay, so do you remember this force that we now understand as being due to quantum chromodynamics? That was invented in 1973. Before that, people were very confused by the strong force. And without going through the whole history of that, they had come up with some formulas. They had actually come up with the formulas for the scattering that were Euler gamma functions. And someone said, oh, these would come out if you assumed that these quarks, no, not quarks, sorry, if protons or mesons were made out of strings. But there, yeah, it was kind of just, kind of came out not unexpectedly. There was one problem with this string theory, though. It predicted the existence of baryons or mesons that had spin 2 and were massless. And everyone knew there were no spin 2 massless particles in the strong interactions. And so they tried all these things to get rid of these spin 2 massless particles, and they just couldn't get rid of them. Well, Guy's laughing because he knows that a spin 2 massless particle is called the graviton. But it took probably about 5 or 6 years before someone said, hey, maybe we could repurpose this string theory, which was originally intended to solve the strong force, and use it for gravity. Now, it turned out it had some other problems. I mean, 10 dimensions is one problem. But there were other problems, and it wasn't until 1984 involving something called anomaly cancellation. And it turned out, which is kind of a technical mathematical problem that would have killed the theory. And then it turned out that in 1984, Green and Schwartz figured out that for certain gauge groups, the anomalies were absent, and then that led to what was called the second string revolution. So strings were invented in the late 60s and then basically tossed into the trash can, except that a couple of guys, a couple of 3 people, continued to work on it. Everyone said that you're wasting your time. This was one of those inspirational stories, right? Green and Schwartz were really stubborn, and they continued to work on it, but everyone said you're crazy, and by the way, you're not going to get promoted. So, so John Schwartz was like a postdoc for like 15 years at Caltech. And Michael Green was some small university. And then they discovered anomaly cancellation. And then suddenly they promoted John Schwartz to full professor. Michael Green got called to Harvard, to Cambridge, and then Ed Whitman got in on the game. So lots of interesting historical tidbits.
Does it make sense to ask what strings are made of?
Nope. Because
why?
You know the answer. I mean, the infinite regress. I mean, it's turtles all the way down. So no, just like with point particles, we think of, with particle theory, we just think of point-like objects, and with strings, all you're telling is that there's some dimension to them, and then you add the magic of quantum mechanics. So strings would be where it starts. Now you could ask another question, which was, do we know whether they're strings or maybe they're membranes, right? Why just have 1 dimension? Why not 2 or 3 or more, right? We've got 10 dimensions to play with or more. And then we have to get into the mathematics. It turns out that it's very difficult to go beyond 1-dimensional objects with strings and still have your theory be mathematically consistent. See, theoretical physicists are always balancing between, we basically have 2 criterion. We want to be following experiment, we want to be in consistent with all experimental results, but we also want to be mathematically consistent. And you have to have a mathematical framework that's self-consistent. And it turns out that it's actually not that easy to satisfy both of those constraints. So that kind of keeps us on track. As I said, we could use a little more help from experiment right around now. But the mathematical consistency puts some pretty strong constraints on. Grace, I saw you had your hand up.
Yeah, I was just wondering what area of theoretical physics you particularly do. I think you did string theory.
I have done some string theory. Right now I'm doing something a little different. It's related. I mean, the thing is, even though string theory we haven't been able to make it work out yet as a theory of everything, we've gotten a lot of side benefits from it. It turns out that we've learned a lot, and it allows us to solve a lot of other problems. So what I'm working on is, remember I told you about that strong nuclear force, the chromodynamics. The thing is, the problem with a strong force is it's very hard to do calculations with it. I told you we can't calculate the mass of a proton, knowing that. So we'd like to understand more about it. There's a sense in which there's more to the theory than we understand. So we can write down the basic framework, we can do some calculations with it, but there's more about it. Often the mathematical structure has more symmetries in it than we realize at first, and we're starting to see signs of that. So that's kind of what I'm looking at. New symmetries in the strong interaction that might allow us to calculate things like, well, I mean, I say the mass of the proton, that would be wonderful, but you know, results of experiments that we can't calculate now. But you know, we kind of try to follow. You know, if someone writes a really interesting article on a new mechanism for symmetry breaking in string theory, I'll probably start looking at that.
If I remember correctly, you said that like we don't understand why different particles have different mass, but doesn't Higgs field allow us to describe that?
The Higgs field, so I don't want to get too much into this, but it's true that the symmetry breaking is what gives particles masses, but it doesn't explain why the particles have the masses they do. In other words, there's some parameter associated with each particle that's different, and it's the differences between those parameters that give the different masses. And that we don't know. As I said, there's 17, 20 parameters that are just, you would measure them, but we can't predict them. Kristen?
So, does string theory help understand dark energy, or is
Ha
dark
ha.
energy just sorry.
Not yet. Dark energy, so
Is that like outside of the four field? I mean,
no. So I haven't talked about so I talked about how everything, okay, I talked about how all the experiments agree, a standard model agrees with all the experiments, but I haven't talked about some cosmological results. And we know now that the energy of the universe, we know that everything that we see and can measure, that we see, or one way or another, is only about 4% of the total energy of the universe. There's another 26% or so is dark matter, and then the rest is dark energy. The problem is we can only detect these things gravitationally. Otherwise, they're completely, that's why they're called dark. We can't detect them through the strong force. We can't detect them through the electromagnetic force. People are really hoping that we might be able to detect them through the weak force, and there are a lot of experiments out there now that are trying to detect them, dark matter in particular, through the weak force. But we have no guarantee whether we'll see anything. We haven't yet. The thing is, we know there's a lot of stuff out there, but it's really hard to know anything about it other than its gravitational interactions. And as I said, that's so that's another thing that another area that we would like to learn more about. But it's tough. It's tough. Yeah. No, and in principle, we would like to be able to explain that dark energy and dark matter, but I don't want to say, you know, it's all speculative at this point and no real definitive results. So it's very interesting, but no, I have nothing to report.
So Steve, does that mean that the theory of everything, or the theory that you've just described, explains about 4%? Because the other 6% we can't see
I told you,
yet?
we don't understand the theory well enough to tell.
Oh, so less than the 4%. Okay.
No, it should explain everything, because it is a theory of gravity, so that should be part of the story. But yeah, sorry, I'm kind of telling you, you know, there's only so much we can do. Paul?
Is there any technological application anticipated to string theory, or is it just a purely theoretical exercise? Is not the right word.
Well, I don't quite agree with, I mean, I think it's, you know, at this point, we don't even understand it theoretically well enough to be able to say what it predicts. And if we did, you might expect that somewhere down the road, there might be some applications. I mean, usually the applications follow long afterwards. you know, quantum mechanics at the beginning of the 20th century looked pretty theoretical, and it's behind transistors and cell phones and all of our modern technology. You might have thought that general relativity and the bending of light was pretty abstract and had no applications, but the GPS system would not work if we did not understand general relativity. It uses corrections from that. So, you know, there's quite a lag time, but there's no telling. I mean, I haven't, you know, Higgs bosons, you can say, what are the applications? I mean, we know the Higgs bosons are there. No applications yet. Dave.
Just to talk a little bit about the context of your work and the people you work with. I guess I've learned in later years that science is not just great people doing things by themselves, but it's an extremely collaborative, cooperative enterprise. And you've gone to these international conferences on string theory. So is the theoretical physicist community global? Is it totally open? Is it collaborative? Is there a politics to it, or is it?
Wow. Well, it is certainly international, and it's actually one of the nice things is we have this thing called the archive, which is a way of sharing research, and it's a free thing. And when you submit your work to the archive, it's not peer reviewed, so it's buyer beware, but it's immediately accessible to anyone who wants to look at it. So in a sense, it's very open, right? It's not, people don't hide their results. They want, in fact, you want people to be working on what you've figured out. So that's a very good thing. In fact, I must say that when I came to Bowdoin, one of my concerns was that I would not have access to sort of cutting edge research. But right around, you may have heard of something called the World Wide Web, and browsers and so forth. Right around 1993, 94 is when that became possible. And so coming to Bowdoin, I was able to know at the same time as my colleagues at big research universities what the research was. So and that's a very good thing. There are probably other issues, but I think maybe it's late to be getting into all of those right now. In fact, maybe this would be a good time. Maybe we'll take one more question, because I don't want people to.
I think I can speak loudly enough. Steve, you talked about how things have evolved towards, you know, string theory and people struggling with that to try to make sense of it. Is there a competing theory out there besides string theory that would explain this, you know, this grand unification?
Well, let's just talk about the gravity, right? There are a few other approaches. They're not as well known, and in my opinion, they're not as well developed. So, you know, there's something called quantum loop gravity, which attempts to look at a notion of space-time foam, and it's an attempt to do a quantum theory of gravity in that way. It does not try to be a theory of everything, though. It's only a theory of gravity, which would be good enough. I don't know that theory as well, and also I think it also has, I mean, it has some challenges as well. So, you know, the best results happen when lots of people are working on lots of different ideas. I mean, that's kind of what's happened to string theory. In the late 80s, everyone was trying to develop it into the theory of everything and get understand the four forces. And that early hope was dashed upon the fact that we don't understand a lot of things about it. And so people sort of branched into lots of different sub areas, and we've learned a lot of things about a lot of other areas. String theory has been a marvelous sort of technology, if you like. You asked if there are any applications, just mathematical, but those have been substantial. And I believe mathematicians have found that it's opened a lot of new vistas. So I think it's good for people to work in lots of different areas. And if someone comes up with a good idea, you can bet that the rest of us will flock to it. All right. Well, thank you very much for your patience.